Okay, so today we're going to be talking about graphing tangent and its reciprocal function cotangent. So to start off, I'm going to have all of you just go ahead and fill out this table evaluating the tangent function at a number of unique angles on the unit circle. So if you have a chance, pause the video real quick and try to see if you can fill this out. Well, if you went ahead and filled this out, you should get something that looks like this. Let me just kind of fill this in here. And tangent and cotangent are unique and different from sine and cosine for a number of different reasons. But starting off, we definitely see that there are going to be some angles where the function is undefined, negative pi over 2. Since we know that the tangent is y over x, and there are certain places where x is going to be 0, we're going to find a number of different places where the function is undefined. So that's going to have some implications for us in terms of thinking about the domain, thinking about the range, but we'll get to all that. A couple of other values that I just want to make sure that you're aware of. We have a number of different negative root 3 and negative root 3 over 3, and then the opposites of those. I went ahead and wrote those approximate values down below just because we're going to be graphing them, and not all of us know right off the bat what something like root 3 over 3 is equal to. I went ahead and did the same for cotangent. Now you'll notice that the table for cotangent is a little bit different, whereas for the tangent of x, I started at negative pi over 2. For cotangent, I started off my table at 0. And I could have started in a number of different places, but I started at 0 because, again, I want to reiterate that cotangent is the co-function of tangent. So it's effectively going to be the tangent graph horizontally shifted over 90 degrees or pi over 2 radians. So I have my table start off at 0. You could have started at a number of different places, but I did have it here listed at 0. So now that we have a couple of values for tangent, we have what we need to go ahead and start graphing. Let's kind of categorize a couple of our unique values. First off, where do we have vertical asymptotes? Well, that's effectively asking where is our tangent function undefined? Well, we notice here we have undefined values at x is equal to negative pi over 2 and pi over 2. We see that tangent of x is equal to 0 at x is equal to 0. We have x is equal to 1 at, tangent of x is equal to 1 at x is equal to pi over 4, and negative 1 at negative pi over 4. Okay. Now what I'm trying to do here is I'm trying to come up with my 5 key values, or my 5 critical values that I'm going to be using when I graph my tangent function. But you'll notice here that tangent of x being equal to 1 or negative 1, that these are not maximums or minimums. And we'll see graphically what this looks like, but they are ones that I want to use to help graph. Now let's look at cotangent. Where is my cotangent function undefined? At x is equal to 0 and pi. Cotangent of x is equal to 0 at x is equal to pi over 2. X is equal to pi over 4 for this value here, and x is equal to 3 pi over 4 here. Now, is cotangent of x equal to negative 1 in a number of other places? Yes, in an infinite number of other places, in fact. But this is what we're using for our parent function as a starting point for us to graph. So let's start with the tangent graph first, and let's just go ahead and see what the parent function tangent x looks like. Well, I'm going to go ahead and start by labeling my y-axis. Now again, our maximum minimum values, unlike sine and cosine, are not 1 and negative 1, but they are still good markers that I want to have labeled on my y-axis. For my x values, I see that we have vertical asymptotes occurring at negative pi over 2 and pi over 2, and they're going to continue to happen every pi radians apart. So let's go ahead and just jot that for now. So let me just go ahead and use an asymptote line here. And let's have something at negative pi over 2. And I'm going to have something else at pi over 2. And I probably should have labeled my axis first before I started drawing the asymptotes. But let's just leave these in here. And then I'll come back and label my x-axis. So let's go back to this. Okay, so we have asymptotes occurring at negative pi over 2 and at positive pi over 2. Okay. We have tangent of x is equal to 0 at x is equal to 0, which is halfway in between. And we know that it hits positive 1 at pi over 4 and negative 1 at negative pi over 4. Okay, so The 5 critical values for tangent work as such. We're going to go from negative pi over 2 to positive pi over 2. At each end of a tangent cycle, we're going to have vertical asymptotes. At negative pi over 4, we hit negative 1. At 0, we have 0. And at pi over 4, we have 1. So when I talked about the critical values for sine, I talked about it being something like intercept, maximum, intercept, minimum, intercept, or mid, high, mid, low, mid. For the tangent function, we're actually going to get asymptote, low, mid, high, asymptote. Now, what's important to note for these is that negative 1, 1, to reiterate, are not maxes or mins. In fact, what's going to happen is our graph is going to get closer and closer to negative infinity. And we're going to get something that actually looks like this. Now, why is this the case? Well, just remind yourself, tangent is a ratio. It's the ratio of y over x. So just think about our unit circle. As we get closer and closer to pi over 2, for example, if I choose a point that's really close to pi over, for the angle that has an angle that's very close to pi over 2, think about your x and y value. Your y is going to get closer and closer to 1, while your x is going to get really, really small. It's going to get closer and closer to 0. And again, what happens as you divide by something that gets really, really, really small? When your denominator gets super small, then your ratio, your output, is going to get very large. So for that reason, tangent is very unique in that its domain has and range have the following attributes. Its domain, unlike sine and cosine, which was all real numbers, our domain is going to be all the values except wherever there's going to be a vertical asymptote. And that happens at every pi radians apart from pi over 2. So at every multiple, effectively, of pi over 2, or pi n radians apart from pi over 2, we're going to have a vertical asymptote. Our range, as we just said before, our range for tangent is actually going to be negative infinity to positive infinity. Because as we get closer and closer to one vertical asymptote, like right here, for example, our y values are going to get closer and closer to positive infinity. As we get closer to this vertical asymptote, then our y values are going to get closer and closer to negative infinity. Okay, so that's our domain and range. Now, what I've graphed here is one full cycle or one full period of tangent. So we're going to say that your period is always going to be, for the parent function, it's pi for the parent. But for every other instance, we can say pi over whatever our b value is, will be the length of one full cycle of tangent. That's the length before it starts to repeat itself. And I'll just kind of write something like the distance between our asymptotes, just as an abbreviation to help remember. And again, our vertical asymptotes are wherever our function is undefined, or what we had written up here, pi over 2 plus pi n. Okay. And remember, n here is just telling you how many different periods apart are we talking about. So it can be both positive or negative. Okay. Let's graph another cycle of pi, or another period of pi, just so we make sure we understand. We know that a full period apart is going to be pi radians, so I'm going to write 3 pi over 2 here. Halfway between that would be pi. Just think of our unit circle. This would be 3 pi over 4. This would be 5 pi over 4. And again, asymptote, low, mid, high. We're going to go ahead and graph something that looks like this. Okay. All right, now let's switch gears and talk about cotangent. So for cotangent, I'm going to refer to these key values here. And again, cotangent is going to be pretty similar to tangent. It's just shifted over pi over 2 radians. But what that's going to make it end up looking like is a little different. It's almost going to look like a reflection. So let me go ahead and label. So I'm going to start here with at 0. And I'm going to graph one full period of cotangent. So I'm going to mark halfway here as being the end of one full period, which was pi radians. So that's where my asymptotes are going to be. And while I'm at it, I'll just label one more. Well, between 0 and pi, we're going to just go ahead and start filling in our x-axis. So this is just basic fractions here. So pi over 4, This would be 3 pi over 4, 5 pi over 4, 3 pi over 2, and 7 pi over 4. All right, I'm going to start by labeling my vertical asymptotes. So I'm going to go ahead and do this. There's 0. There's me at pi radians. There's me at 2 pi radians. Now we're ready to graph our graph for cotangent. So for cotangent, at pi over 4, referring to our table here, we hit, oh, probably should have my y-axis labeled. There we go, -1 and 1. We're going to have our high, we're going to have our mid, and we're going to have our low at 3 pi over 4. Okay. Again, these are not maxes and mins, but just markers for us to accurately graph a cotangent graph. And it's going to look something like this. Okay. So for cotangent, we're going to go asymptote, high, mid, low, asymptote. Okay. So let's go ahead and do one more period. We're going to get 1 or high, mid, low. And it's going to look kind of cubic. And honestly, I could probably graph that a little bit better, but I think you get the idea. So looking at our cotangent graph, let's fill out what we know. Our domain is going to be all real numbers except where we have a vertical asymptote. So how do we express the equation for a vertical asymptote? It's going to occur at 0 and pi radians apart. So I'm going to write 0 plus pi n. If you wanted to just write x is equal to pi n, that's totally fine. It works. So in fact, I'll just even write that pi n down here. Okay, so every pi radians apart is where our vertical asymptotes are going to be. Our range, again, for the same reasons that we talked about with tangent, are going to be -infinity to infinity. And our period is going to be, in this case, same thing. It's going to be pi for the parent function. And for every other transformation, we're looking at pi over b. Okay, so kind of zooming out a little bit here, we're looking at a general sense of what the parent functions for tangent and cotangent look like. We're spending a different lesson on them because, as you can see, they're different from sine and cosine. They look different. They have different attributes and qualities in regards to where the function is defined and undefined and what we know about the period. So I'm going to kind of close with just 2 quick examples. I'll just graph 2 here and then give you an opportunity to think about cosecant and secant on your own in just a bit.